We'll start in 1 minute. Today we'll start the test 4 review. Remember, the test 4 is this Friday. It will be over chapter 11, sections 1 through 9. I won't read all of these to you, but I'll just remind you, when testing series, make sure you review the integral test, the comparison test, the limit comparison test. Then there's the alternating series test. And we also have the ratio test and the root test. And then also remember the divergence test. I think that's on page 727. You don't necessarily need to memorize these tests, but you need to know them well enough to be able to apply them. Okay, on the first page of the test review sheet, on number 1, we have a couple of limits. So compute the limit of this sequence. It's an alternating sequence, -1 to the n, and then n plus n squared over n times the square root of n plus 3. So if we rewrite this, I'll leave the numerator the same, n plus n to the second. But in the denominator, n times the square root of n is n to the 3/2. And then when we compute the limit, or before we compute the limit, we'll multiply by 1 in the form 1 over n to the 3/2 over 1 over n to the 3/2. So we're going to multiply the numerator, n plus n to the second, by 1 over n to the 3/2. If you can read my writing. And multiply the denominator, which is n to the 3/2 plus 3. Multiply that by 1 over n to the 3/2. And then when we do the arithmetic, we'll get so in the numerator, n times 1 over n to the 3/2 is 1 over n to the 1/2. And then n squared times 1 over n to the 3/2 is n to the 1/2. And in the denominator, n to the 3/2 times 1 over n to the 3/2 is 1. And then plus 3 over n to the 3/2. And this is alternating, so we have this -1 to the n. But we can see that when n goes to infinity, the 1 over n to the 1/2 goes to 0, but n to the 1/2 goes to infinity. And since it's an alternating sequence, the limit does not exist. The next one is not quite as tedious. Notice that both the numerator and denominator have n to the second for the term with the largest exponent. So when we compute this limit, multiply by 1 in the form 1 over n squared over 1 over n squared. So we'll multiply the numerator, 3n to the second minus n times 1 over n to the second, and multiply the denominator, 6n minus 2n to the second, by 1 over n to the second. So we're just multiplying by 1. The reason I chose 1 over n squared divided by 1 over n squared is because in the denominator, the largest exponent is n to the second. Okay, in the numerator, when we multiply 3n to the second by 1 over n to the second, we just get 3, and then minus n times 1 over n to the second is minus 1 over n. And in the denominator, 6n times 1 over n to the second is 6 over n. And then minus 2n squared over, or times 1 over n squared is minus 2. And when we compute the limit, the 1 over n and the 6 over n, those go to 0. And so the limit is 3 divided by negative 2, or negative 3/2. Okay, in number 2, we have infinite series. These are geometric series, both of these in part A. So we can rewrite this one in part A. We can factor 3 out and write it as 3 times 1 minus 3/4 plus 9/16 minus 27/64, and so on. The common ratio is negative 3/4. And so in sigma notation, starting at n equals 1, we can write this as 3 times the common ratio, negative 3/4 to the n minus 1. Okay, so this is in the, the formula for a geometric series. The common ratio is between negative 1 and 1, so it's going to converge. And it's going to converge to 3 divided by 1 minus negative 3/4. So this 3 in the numerator is the same 3 that we're multiplying here. Okay, so when you do the arithmetic, you get 3 divided by 1 minus negative 3/4 is 1 plus 3/4, which is 7/4. And then that simplifies to 12/7. Okay, the other geometric series, if we factor 5 out, we have 5 times 1 plus 3/2 plus 9/4 plus 27/16. This time the common ratio is 3/2. And since that is greater than 1, we conclude that the geometric series diverges. Okay, moving on to problem number 3. Determine if the following series converge or diverge and give an explanation. Okay, so we have some tests that we can use to determine if these series converge or diverge. This one, notice if you just focus on the term with the largest exponent in the numerator and the term with the largest exponent in the denominator, 3n over n to the third, that simplifies to 3 over n to the second. So if we do a limit comparison test with the series where the terms are either 3 over n squared or just 1 over n squared, we might get a result. So if we, I'm just going to use the limit comparison. With the series where the terms are just 1 over n to the second. So in the limit comparison, if we get a positive number as the limit, then that means both of the series do the same thing. We know that this series, where the terms are 1 over n to the second, this is a p series. The value of p is greater than 1, so we do know that this converges. Okay, so in the limit comparison, we divide one of the terms from the series by the other. So in this one, we can divide 3n plus 1 over n to the third plus 1, divide that by 1 over n to the second. So I'll see if I can do a couple of things at once. When we simplify this complex rational expression, we're going to end up multiplying this numerator, 3n plus 1 over n to the third plus 1. We'll multiply that by the reciprocal of 1 over n to the second. So in other words, multiply 3n plus 1 over n to the third plus 1 by n to the second over 1. Do you see that? So when we do that, in the numerator, 3n plus 1 times n to the second is 3n to the third plus n to the second. And in the denominator, 1 times n to the third plus 1 is just n to the third plus 1. So perhaps we know just by looking what this limit is. So in the denominator, we have n to the third is the term with the largest exponent. And in the denominator, the term with the largest exponent is n to the third. So when computing this limit, if we'll do the same thing that we did earlier today, we'll multiply by 1 in the form 1 over n to the third over 1 over n to the third. So I can try to write that down in the space. So I'll give it a try. Limit as n goes to infinity. We're going to multiply this numerator by 1 over n to the third. So let's just do that in our heads. 1 over n to the third times 3 n to the third plus n to the second. We'll get 3n to the third over n to the third, which is 3. And then plus n to the second over n to the third is 1 over n. And in the denominator, multiply n to the third plus 1 by 1 over n to the third. We get 1 plus 1 over n to the third. And now we can take the limit. The 1 over n goes to 0, 1 over n to the third goes to 0. So this limit is positive 3. And according to the limit comparison test, if the limit of the ratio of the terms from the sequences is a positive number, then both series are either convergent or divergent. Since we know that the series of the terms 1 over n to the second converges, then we also know that the original series converges by the limit comparison test. Okay, in part B, determine if this series converges or diverges. The terms are 2n minus 1 over 3 plus 7n. So what do you think? So the thing that I think about, well, the numerator has 2n and the denominator has 7n. If I just take the limit of the terms 2n minus 1 over 3 plus 7n, I get a non-zero limit. So the test for divergence says the series is divergent. Right? So in general, if you're testing a series, if you can look and tell just by looking that the limit of the terms is non-zero or doesn't exist, then the series diverges by the test for divergence. So this limit, the limit of 2n minus 1 over 3 plus 7n, is equal to 2/7. And since that does not equal 0, the series diverges. I guess I can put the there. The series diverges. And we applied the test for divergence. All right, the next one, part C. The series, the terms are pi to the n divided by 4 times e to the n minus 1. So the n minus 1 is the exponent on e. So what sort of series is this? What kind of series is it? Well, it's sort of camouflaged, but this is just a geometric series. If we rewrite it this way, the denominator has e to the n minus 1. The numerator has pi to the n. But if we take one factor of pi, so pi over 4, and then times pi to the n minus 1 over e to the n minus 1, then we can write this as the series, the terms are pi over 4 times pi over e to the n minus 1. Okay, so this has the familiar form of a geometric series. And all we're trying to do is determine whether the series converges or diverges. So what about this one? What's the common ratio? Pi over e is the common ratio. Pi is about 3.14159. E is about 2.71828. So this common ratio is greater than 1. So that means the geometric series diverges. And that's all we needed to do on that one. Okay, the next series, the terms are n to the second over e to the n. So what should we do on this one? There may be more than one way to go about it. So for this one, I want to try the ratio test. So remember, the ratio test involves the limit of the absolute value of the n plus first term divided by the nth term from the sequence in the series. And if that limit is less than +1, then the series converges. If it's greater than 1 or infinite, then it diverges. Okay, so the n plus first term is n plus 1 to the second over e to the n plus 1. Divide that by the nth term, which is n to the second over e to the n. We can remove the absolute values because all of the terms are positive. We'll get n plus 1 to the second over e to the n plus 1 times e to the n over n to the second. Okay, so I'll rearrange the terms a little bit. We'll have n plus 1 squared divided by n squared. We can think of that as n plus 1 over n squared. And then e to the n divided by e to the n plus 1 simplifies to 1 over e. Hey, what does the limit of n plus 1 over n to the second go to? We could put the limit on the inside and then square the limit. So the limit of n plus 1 over n and then square it. What's the limit of n plus 1 over n? So maybe I should do that. 1 over e is a number, so we're just 1 over e is unaffected by n. So we can put 1 over e times the limit of n plus 1 over n, and then afterwards we'll square that limit. So we can rewrite n plus 1 over n as 1 plus 1 over n. And the 1 over n part goes to 0. The other number is just 1. So the limit of n plus 1 over n is just 1. And 1 over e times 1 squared is 1 over e. We're using the ratio test. 1 over e is less than 1. And so the series converges because using the ratio test gave us a limit that's less than 1. So the series converges. Okay, that's page 1. Let's go on to the next page. This is more of the same. Determine which of the following series converge. Justify your answers. Indicate which convergence test is used and include all appropriate computations. So this is sort of what you'll want to be able to do for test 4 on Friday. If all you say is that a series converges without any justification or with no computations, well, you might get a point or 2 if you're correct. So on this one, the series where the terms are the square root of n plus n to the second over n to the third plus 2n. So any ideas on how to determine if this converges or diverges? All right, the thing that catches my attention, the term in the numerator with the largest exponent is n to the second. The term with the largest exponent in the denominator is n to the third. N to the second over n to the third is equivalent to 1 over n. So my thinking is maybe the limit comparison test with the series of the terms 1 over n. So limit comparison. With the harmonic series, where the terms are 1 over n. Okay, what do we know about this series? Does it converge or diverge? Yeah, this one diverges. And so when using the limit comparison test, we compute the limit of the ratio of the terms from the sequences. And if the limit is a positive number, then that means both series do the same thing. In this case, if that's what happens, both series will be divergent. Okay, so for the limit comparison test, not to be confused with the ratio test, because we're comparing 2 different series. So the term from one of the sequences, the square root of n plus n squared over n to the third plus 2n, we divide that by the terms from the other sequence, which is 1 over n. Then we'll simplify this complex rational expression. So we get the square root of n plus n squared over n to the third plus 2n multiplied by n over 1. Okay, we'll simplify a little more. The denominator is just n to the third plus 2n times 1, so n to the third plus 2n. And in the numerator, the square root of n times n is n to the 3/2. And then n squared times n is n to the third. Okay, so when we get to this point, we know what that limit is. What's the limit? Okay, it's that same old trick. N to the third is the term with the largest exponent in the denominator. So we multiply by 1 in the form 1 over n to the third over 1 over n to the third. N to the 3/2 times 1 over n to the third is 1 over n to the 3/2. N to the third times 1 over n to the third is 1. And in the denominator, n to the third times 1 over n to the third is 1. And then plus 2n times 1 over n to the third is plus 2 over n squared. As n goes to infinity, 1 over n to the 3/2 goes to 0, and so does 2 over n to the second. So this limit is positive 1. So what does that mean? Well, in our limit comparison, we were using a series that we know diverges. And according to the limit comparison test, if the limit of the ratio of the terms from the two series is equal to a positive number, then both series do the same thing. Since the series that we tested it with diverges, then this series also diverges. Okay. So this series diverges. All right, the next one, part B. The infinite series, the terms are 2n times e to the negative n to the second. So what series test comes to mind?
The ratio test?
The ratio test? I don't think I tried that on this one. It might work. I have something else in mind that I think, well, in my opinion, might be more efficient. I'll try using the ratio test sometimes. This one, though, I'm thinking the integral test So if we think of this function f of x as 2x times e to the negative x squared, it's easy to show that this function f is positive for values of x from 1 to infinity, and it's also decreasing. And so the integral test can be used so the conditions for this function, it has to be positive and decreasing. Positive and decreasing on the interval from 1 to infinity. And the integral test says if the improper integral from 1 to infinity of 2x e to the negative x squared dx, if this converges, then the infinite series also converges. And the integral test also says if the improper integral diverges, then the infinite series also diverges. Okay, so on this one, to compute an antiderivative, we can use the substitution rule. If we assign u to be negative x squared, then du is negative 2x dx. We see the 2x dx, we just are missing a negative sign, so negative du is our 2x dx. Okay, so when we make substitutions, I'll put the negative sign out front. And we have e to the u du. And then the limits of integration, when x is 1, the u value is negative 1 squared, or negative 1. And as x goes to positive infinity, the u values go to negative infinity. So we have the negative of the improper integral from negative 1 to negative infinity of e to the u du. So using a property of integrals, we can change the negative to a positive if we switch the limits of integration around. So the lower limit will be negative infinity, the upper limit will be positive infinity, and then e to the u du. All right, so what I'm going to write next is quite a bit informal, but since I'm running out of space, an antiderivative of e to the u with respect to u is e to the u. And then the limits are from negative infinity to negative 1. So when u is negative 1, e to the negative 1, and then we subtract what e to the u becomes as u approaches negative infinity. So I really shouldn't write this, but e to the negative infinity what does that number, or what should I replace that number with? This is like 1 over e to the positive infinity. So e to the infinity is infinity, 1 over infinity is 0. That's the point. So the limit does exist. The limit is equal to, or the value of the improper integral is 1 over e. So in other words, the improper integral converges to the finite number 1 over e. So that means that series also converges. Okay, let's move on to the next one, part C. The series, the terms are -1 to the n over the natural log of n. Okay, does anything come to mind on this one? Yeah, it is an alternating series. And then if you compare in absolute value, the n plus first term, the absolute value of the n plus first term, 1 over the natural log of n plus 1 is less than 1 over the natural log of n. And the limit as n approaches infinity of 1 over the natural log of n equals 0. So both conditions of the alternating series test are satisfied. So by the alternating series test, the series converges. Okay, the next series, the terms are 1 over n times the nth root of n. Well, how about limit comparison? Limit comparison test with the harmonic series. So if that doesn't work, we'll try something else. Okay, so we take the limit as n approaches infinity of the ratio of the two terms, or the ratio of the terms from the two sequences. So we can write 1 over n times the nth root of n over 1 over n. When we simplify this, the n's are going to cancel and we get 1 over the nth root of n. So what does the nth root of n go to as n goes to infinity? So if we can find the limit of the nth root of n as n goes to infinity, then we'll have our answer. So that's what it comes down to. This might look familiar. So I'm just focusing on the limit of the nth root of n, ignoring for the moment that it's in the denominator. But the nth root of n can be written as n to the 1 over n. When you recognize what we're doing, then just throw in the towel and we'll move on. Since n is positive, we can replace n with e to the natural log of n to the 1 over n. And then using properties of exponents, we can write this as e to the natural log of n over n, because 1 over n times the natural log of n is natural log of n over n. So as we let n go to infinity, this exponent becomes infinity over infinity. So we apply the L'Hopital's rule to that. So this will be the limit as n goes to infinity. So when we use L'Hopital's rule, the derivative of the natural log of n is 1 over n. The derivative of n with respect to n is 1. So we have the limit of e to the 1 over n. And as n goes to infinity, the exponent 1 over n goes to 0. And e to the 0 equals 1. So this limit equals 1. What does that mean? We're trying to determine if this series converges or diverges. Yeah, it diverges. We use the limit comparison test with a series that diverges. And the limit comparison gave us a limit that's positive. So that means both series do the same thing. So this series diverges. Okay, the next example. In part E, the terms are negative 5 to the n over 1 plus 3 to the 2n. We can do something in the denominator that might make it look a little better. Three to the 2n that's the same as 3 to the second to the n, or 9 to the n. It's not required, but it might be easier to think about when you write it this way. So does anything come to mind? The root test? Yeah, the nth root of 1 plus 9 to the n, we have to take the nth root of the entire denominator. That doesn't work out too nicely, as nicely as we would like. Yeah, we could use the ratio test. I want to use the alternating series test. It is an alternating series. So we have to, in order for the alternating series test to indicate that this series converges, then 5 to the n plus 1 over 1 plus 9 to the n plus 1 has to be less than 5 to the n over 1 plus 9 to the n. In a few algebraic steps, you can show that this inequality is true. It's like 4 or 5 steps. You can be convinced that this inequality is true for all n. So the absolute value of the terms decreases. And then the limit has to be equal to 0. So the limit of 5 to the n over 1 plus 9 to the n we have to convince ourselves that this limit is 0. Okay, but note that 5n over 1 plus 9 to the n, all of the terms are positive, but this is less than the limit of 5 to the n over 9 to the n. Right, this denominator, 1 plus 9 to the n, is bigger than that one, so that means the fraction is smaller, right? And the limit of 5 to the n over 9 to the n, you can think of that as the limit of 5/9 to the n. And a number that's between 0 and 1 with an exponent n, as n goes to infinity, that limit is 0. So the limit of 5n over 1 plus 9 to the n must also be 0. Okay, we're out of time. This series converges by the alternating series test. Okay, we'll work on more problems tomorrow. So go ahead and sign in for attendance.